Hello, my name is Aaron Balke, and in today's video I'm going to be breaking down my dimensional reduction assessment for my Master's in Data Analytics. This assessment uses PCA, Principal Component Analysis, in order to do dimensional reduction. I hope you enjoy. For this assessment, I wanted to see what's the minimum amount of For this assessment, I wanted to see what is the minimum amount of principal components required to capture 80% of the variance in order to explain 80% of the variance in our data set. And the goal is to maintain a high level of variance while lowering the dimensionality. This will simplify future analysis, this will increase the efficiency of our analysis, and my goal is 80% because of that. Principal component analysis is a dimensional reduction method which takes the original features and then uses different combinations of those features to flatten it down and linearly lower the dimensionality of it. And so that's the reason we're using principal component analysis, is to hopefully get that lower dimensional data. We gotta have normalized and standard data for our PCA. Since this analysis does maximize variance, unscaled data would have crazy magnitudes that are not effective for lowering the dimensionality of it. And the reason for that is it would cause skews in the data and all that sort of nonsense. Another thing we gotta worry about is that we can only use continuous variables when it comes to PCA. So our original data set had about 50 different features. It's a hospital data set and of different patient records and all, and unfortunately we're only able to use, I believe this is seven features of our original 50 variables. So not as many features as we started out with. So first thing we're going to do is import pandas, numpy, pyplot, seaborn, all the standard imports. We're going to get those in here, and then we are also going to import from sklearn the standard scaler in order to scale our continuous variables, and the PCA object in order to do the PCA. Then I have a data frame, our data frame import data as a data frame, and I hold it to be just those 7 continuous variables. At this point, I wanted to check for feature correlation. I wanted to see if there were correlations between independent variables. This is something we don't want, because too high of correlation would sort of like how having the magnitudes of variables be different, the scaling be different. If we had 2 variables both with really high correlation with each other, then keeping both of those would also skew the data set. So I ran a Pearson feature correlation on this data, and what we're able to see is they all are pretty much uncorrelated except for total charges and initial days, which are 99% or have a 99% correlation. So we do have to drop one of those. I decided to drop total charges, so we just dropped total charges from the data frame because it has such high correlation. I guess it's important to note, if you don't know about Pearson correlation and heat maps, these correlation values in the center are just correlations to themselves. So latitude's correlation to latitude should be 1. If it's not that, something terrible has happened. So that one line of ones we don't need to worry about. But this 99% here between total charges and initial days we do have to worry about. I then decided to use standard scaler in order to do the scaling. There's a couple different ways of doing this, but standard scaling is nice because it sets the standard deviation to be 1 and the mean to be 0. So it fits it between -1 and 1. And as we can see from the output here, that is what happens. All of the standard deviations is set to 1, and all of the means are set to 0, or -0. So for the actual analysis, we're going to first print off the component matrix And the way we're going to get that is by running PCA. We have 6 components. Those are the 7 continuous variables minus the total charges, which was highly correlated. So we just have 6 variables at this point. So we input the scaled data frame, which is just 6 components, into our PCA object, and we run a transform on it. We fit it and transform it on that scaled data frame. Then we get the principal components. That's just, I've just ran a set of columns as the names for the principal components. So PC1, PC2, PC3, PC4, PC5, PC6. And we get those components out from the data frame made from the principal components with those names. The loading matrix is then made based on those principal components. And so that tells you, this sort of shows you how much each variable is being applied to that principal component. So we can see that the latitude variable is really being used on this first principal component. We can see that, I guess also the longitude, but in a negative correlation sense, is being used a lot on this one as well. And we can see the additional charges isn't even being used on this first principal component. So that's what we're able to see from this loading matrix. When it comes to identifying the key principal components, which of these components are ones that we need to keep? We're going to use the Kaiser rule, which says using, I believe it's pronounced EN values, anything greater than 1 is considered significant, and anything less than 1 is considered insignificant, and we can discard those principal components. So using a covariance matrix, we shove that into the E9 variable calculation here, and this uses dot products and all. Dot products are scary to me, so we're letting a NumPy do all the dot products work here, but that's what's happening here, and that's how we get the E9 values back out for each variable. So we are able to plot this graph here. We have the red line, which is that using the Kaiser rule, any principal component above this red line is considered important. Anything below is considered not so important for keeping track of variance. And what we came back with, when it came to the 3 and 4 value, it was getting kind of close, so I did print out the values themselves. We can see that principal component 1, 2, and 3 have a value higher than 1, and principal 4, 5, and 6, principal component 4, 5, and 6 have values less than it. That means that for, according to the Kaiser rule, the only variables we need to keep are 1, 2, and 3. Now, using those variables, the next thing we need to do is figure out, for each of these variables, how much of the variance is being explained. And so using a for loop, running through the loadings and getting the explained variance from each principal component, explained variance ratio, all of that sort of good stuff, we're able to get out a explained variance and cumulative explained variance. We also have the total variance. This is using the Kaiser rule, using PC1, PC2, PC3, what the value is. But what we're able to see is with all of the components, or excuse me, with the 3 components we do want to keep, according to the Kaiser rule, we're only able to keep a explained variance of 52.35%. So if we just keep if we're able to just keep the first 3 Kaiser rule chosen principal components, we will only be able to explain 52% of the variance, only around half of the variance. And so this doesn't answer our research question, which was how many principal components are required in order to keep track of 80% or more of the variance. And using this little plot here, this little graph here, we're able to see that 5 principal components are required for that. So in order to keep track of, in order to answer our question, we do need 5 principal components in order to keep track of 80% of the variance. Now, for answering my research question and the next conclusions we can make is, if we're really, according to my research question, if we're wanting to keep 80% of the variance, but we're going to need 5 principal components for that, that really, we started with 7 variables and we're only able to get down to 5 principal components. We'll have to really take into account if that's a thing worth doing in our situation. That's sort of the next step, is figuring out if that is worthwhile. Using the just 3 principal components, that only explains 50%. So that's something that may be useful for other analysis, but for answering our research question, the next question would be, is it even worth doing the principal component analysis and all that sort of stuff? So that's sort of the results of the analysis and my conclusions from this principal component analysis. I hope you enjoy and have a good one.